Good morning. Today we'll be covering chapter 17. And we should get through all of it. We got through all of it in the first class. Your exams will be released after class in the resource or outside of the resource center in the normal location. I'll also post a key online for them. So today I am talking over chapter 17, which is kind of an introduction to aromatic rings. Chapter 18 is really much more aggressive when it comes to actual reactions of them. Oops, wrong end. This is more just like talking about what an aromatic ring is and doing a few reactions, which are pretty normal for you guys. They're like SN2 things with the benzene ring, kind of stuff like that. So our most common aromatic ring that you guys have dealt with up to this point is going to be benzene, which is just a cyclohexane with 3 double bonds to it. You've been told it's aromatic. Today we're going to talk a little bit more about why. So we also have, if we have some substituents on there, they're going to be kind of what you expect. So if we add a chlorine to this, this would be chlorobenzene. It's 2 different words. There's a space between chloro and benzene. Same thing for a nitro group. So NO2, give me nitrobenzene. If I have a carbon chain, like a methyl or a propyl or an ethyl, this would be propylbenzene for this one. So nothing overly shocking there. There's a bunch of common names that you guys are going to see a lot. I'm going to go through, the book has like 10 of them. I'm going to only go through 5 of them because a bunch of them we don't really talk about that much. So the first one is toluene, which is really just methylbenzene. But we use it so much that it gets its own name. The next one is phenol, should be hydroxylbenzene. If we have an aldehyde or carboxylic acid, so carboxylic acid could be benzenoic acid. And aldehyde is going to be benzaldehyde. I'm sure it's one you guys have heard by now. The last one I usually talk about is just styrene. They make styrofoam. It's an ethylene with benzene. And we may or may not get to it today. These are some common names. Something that's a little bit more important, and we're going to talk about it a lot starting on Monday when we talk about chapter 18, is the different positions relative to your substituent or your main. So this is toluene here. We have this methyl group. Normally we would kind of number 1, 2, 3, 4, 5, 6 around our ring. When we have a benzene ring, we're going to do this differently. We are going to, because it's so symmetrical, have 3 different positions. So the first one is this position that is 1 carbon away. This is going to be referred to as the ortho position. We have the position that's 2 carbons away. Again, we'll have 2 of them. This is called the meta position. And our last position is going to be the one that's opposite to our toluene group. And that's going to be called our para position. And if we had two substituents, like this here, we could refer to this as ortho chlorotoluene. We could also call it orthomethyl chlorobenzene. There's not really a priority list for these. Usually you just do the one that gives you the shorter name. So toluene is easier to say. If I put it in the position next to that, meta position, this would be meta chlorotoluene. And putting it on the bottom position, would give me parachlorotoluene. These are often abbreviated to just like O, M, and P. So you'll also see that a lot. No space between chloro and toluene for this one. Okay, so that's naming for these. And it's more just, I don't think I'm actually gonna have you guys do actual naming. It's just when we get to reactions, we're gonna be adding them to these different positions here. So you need to be able to recognize quickly, is it going ortho versus para versus meta kind of a thing. So the majority of what we're going to talk about today is this concept of what is an aromatic ring. So if we look at benzene, this is considered aromatic. And one of the main reasons it's aromatic is because it's incredibly stable. A lot of that comes from the fact that you have basically a constant resonance cycle you can do. So these electrons can move. I'm going to move counterclockwise. Get a different resonance structure. And I could keep doing this infinitely. You can always kind of like keep moving these around in this circle for as long as you wanted. It's this cyclic system where your pi electrons have all lined up. So if I looked at my pi electrons, I can draw double bonds in these positions, but there's no reason I couldn't just keep moving those electrons around the ring. And that gives you like an incredible amount of stability. So there's some rules for things to be aromatic. And one thing that it has to have is, so it has to be cyclic. If I was to have just this here, where we have the same thing, it's a 6-carbon chain, it has 3 double bonds to it, but your electrons can't kind of move in that cyclic motion, so they're not going to be, this is not aromatic. Probably shouldn't come as a surprise to you. Your aromatic rings are always some sort of cyclic systems. They also have to be conjugated. So if we have this here where we have an sp3 center, this is going to be not aromatic also. Because our electrons can't move through this center here, we're only kind of doing the same thing we were here, where electrons can move back and forth, but they can't move in a cyclic motion. The last thing that's important is going to be what's going to differentiate between aromatic and anti-aromatic. And I'm not going to talk too much about what an anti-aromatic compound is. It's essentially the opposite. An aromatic compound is extremely stable, and anti-aromatic is extremely unstable. But I'm going to give you kind of a rule as to how we determine if it's one or the other. So for it to be aromatic, it has to follow what's called the Huckel rule. Which is where your pi electrons are going to equal to 4n plus 2. And I'll go over what that means in a second. So in order to be aromatic, it's going to need to have 4n plus 2 pi electrons. N, again, doesn't specifically like correlate to anything. It doesn't correlate to your number of double bonds or anything. It's just going to give you kind of a range in which all of the aromatics fall into. So for instance, just start plugging in numbers. So if n equals 0, it would have 2 pi electrons. 1 would give you 6. 2 would give you 10, 14, 18, etc. When I look at my molecule, if it has 10 pi electrons, I know it falls into this category versus our anti-aromatics. Which are going to follow just a 4n rule. You're always going to have an even number of pi electrons because they're always paired. So this would be anything with 4, 8, 12, 16, 20, etc. pi electrons. Let's do that. Talk about that. So benzene is usually the example we can start with. It has 3 double bonds. Which means it has 6 pi electrons. If we look at our chart, 6 is over here in the aromatic category, meaning this is an aromatic compound. If we look at a different compound, so let's take this 8-membered ring with 4 double bonds. Because of that, it has 8 pi electrons. We look back at this little chart we made, it's over here in the 8. So it's going to be anti-aromatic. I'll talk a little bit more about this later on, but aromatic compounds are incredibly stable. So if we were to take benzene, put in H2 and platinum, this is going to give us no reaction. You're not going to be able to reduce these. Versus if we take this anti-aromatic, which is highly reactive, and threw in H2 and platinum, it's going to immediately reduce it. And that's really going to be your difference, is that these anti-aromatics are highly reactive. So let's take a look at some other examples. So lone pairs. Versus positive charge. So a lone pair of electrons, especially when it's just on carbon here, we'll talk a little bit differently when we talk about heteroatoms. So like oxygens or nitrogens, they're going to follow slightly different rules. But for a carbon here, these are going to be delocalized. You're able to do resonance with these. They're part of your pi system. Same thing with this positive charge. Because we have this positive here, these are both fully conjugated. They both fall into all of our categories. So you have to look at how many pi electrons they have. This first one here, we have 2 double bonds. And 1 lone pair. All of these are going to get multiplied by 2, so that'd be 4 plus 2, so it's a total of 6 pi electrons. And that's going to make this aromatic. For this one here, we have 2 double bonds. And 0 lone pairs. So a total of 4 pi electrons. And this is going to be anti-aromatic. Our systems can also, they can have bridgeheads to them. That isn't going to like affect anything. So if I was to have this here, this still falls into our normal rules. We're just going to count the number of double bonds: 1, 2, 3, 4, 5. So 5 double bonds, 10 pi electrons. That's part of our aromatic category. So I'm going to give you guys about 4 of these, have you guys go through them and list whether that they're anti-aromatic or aromatic. And I'll give you guys maybe 3 or 4 minutes to do them. They should be pretty quick. This is a 7-sided ring, just so you guys can't tell. The first class had a little bit of trouble seeing that. Okay, so take about 5 or maybe 3 minutes, go through these and figure out if they're aromatic or anti-aromatic. All right, so let's count our double bonds. In this first one, we have 1, 2, 3, 4, 5, 6, 7 double bonds. Which means we should have 14 pi electrons. If we look back at our chart, that will put us in the aromatic range. Over here on the right, we have 1, 2, 3 double bonds. We have 1 lone pair. Gives us a total of 8 pi electrons, which makes this anti-aromatic. We have 1 double bond, which means we have 2 pi electrons, which falls in the aromatic category. Last one, we have 1, 2, 3, 4, 5, 6. A positive, which is 0 lone pairs. So a total of 12 pi electrons, making this anti-aromatic. All right, so there's one other thing I'm going to talk about with these is going to be looking at heteroatoms. So if I throw a nitrogen or an oxygen in there, how does that affect things? And this is going to get back to a concept you guys learned about probably in the very beginning of OChem 1. Which is going to be whether or not these electrons are localized versus delocalized. So if you have a double bond, attached to your your lone pair, they're going to be localized, which means we're going to not count them for aromaticity. And I'll re-explain the 4n+2 thing in a minute. Someone asked about it. So for this one here, we have a double bond that's already attached to this nitrogen. We can't really do resonance. If we were to try to move these electrons in, we'd make way too many bonds to this nitrogen and carbon here. So this lone pair is not really allowed to move at all. These are considered localized. So because of that, this is only going to have the double bonds count. So this is just going to have 6 pi electrons. Someone asked me to re-explain the 4n+2 thing. So it's kind of just a grouping. You can either fall into 2 categories. Either 4n+2 or 4n. If you think n equals 0, we would have, so 0 times 4 plus 2 is going to give us 2. 0 times, or 1 times 4 plus 2 is going to give us 6, 10, 14, etc. These are just numbers that will be aromatic. It's not like the number of double bonds will equal n or anything like that. Okay, I think people got it now in line. All right, so this is 6 pi electrons, which puts you into this category here. So this would be aromatic. Our other example, we don't have a double bond currently attached to this nitrogen. So these are considered delocalized. And they're going to end up counting. So I can do resonance here. I can push these electrons down. This negative can be on the carbon. We're going to end up with 2 lone pairs and 1 lone, or 2 pi bonds, 2 pi bonds, 1 set of lone pairs. This is also going to be a total of 6 pi electrons. And is going to be considered aromatic. Oxygen is kind of the ideal candidate for explaining this because it can do both of those concepts. There's 2 different sets of lone pairs on an oxygen. One of them, if we have this furan system, is going to be localized and one of them is going to be delocalized. So currently we're starting with, there's no double bonds attached to this oxygen here, which means one of these lone pairs can be delocalized. It can move in to do resonance. I'm going to get what looks like. This here. Now my oxygen has a double bond attached to it, which means that this other set is going to be localized. So if I draw this out in its own page with the other two nitrogen compounds, when we look at this furan ring here, one of our two pairs of lone pairs is going to be considered delocalized. The other pair is going to be localized. We count the delocalized ones for our pi system. So this is 6 pi electrons. We look at the nitrogen version of this. We've only got one set of lone pairs. These are delocalized. This is also 6 pi electrons. And then the pyridine version. Our nitrogen already has a double bond. No, I want this in green. So these are localized. Therefore, this is also going to be 6 pi electrons. All of these are aromatic, even though they have different lone pair situations to them. So hopefully that's a little bit of a refresher of localized versus delocalized. We're just applying those rules to figure out if it's aromatic or anti-aromatic. Let's do some simple reactions involving aromaticity. So the first one is if we take chromic acid, so Na2Cr2O7 in H2SO4 and water. If we take toluene and do this, we are going to oxidize that toluene all the way to benzoic acid. We take the same thing with this isobutylbenzene. H2SO4, H2O. This is such a easily oxidized position. That it's actually going to break your bonds and give you the same thing. So it will oxidize it all the way to the benzoic acid. If we have 3 substituents on there, let's do this. Can oxidize every position to its own carboxylic acid. giving you this tribenzoic acid. The only time this won't work is if you start with a tert-butyl where you don't have any hydrogens to pull off originally. You're just going to end up with no reaction. So it needs at least something to oxidize from. You have to have at least one H on there to be able to pull off. And if it does start oxidizing, it will oxidize all the way through the carboxylic acid and burn off whatever carbons were originally on there. Some other reactions you can do if you throw in NBS. Remember back to chapter 10. You take NBS with a double bond. It will add a Br to your allylic position. We do the same thing with an aromatic ring. You can add that Br to what's called your benzoic position. And that's gonna be this position that's one away from your benzene ring. It's really stable. It's got a whole ton of resonance to it. So same concept. Your book talks about a lot of different reactions, which are basically just SN1s and SN2s you can do next to this position. I'm just going to go through one of them. Let's go. So normally if we had this haloalkane with HCl, going to do an SN1, this would leave. We'd end up doing a rearrangement. You get a Cl here. Oops, I'm gonna drop Br on this one. We do this next to a benzene ring. Because we have resonance to that ring here, we're not going to get any sort of rearrangements. These are just going to do your normal reactions. And you can avoid that. Ebook shows you a bunch of like E1s and other things you can do here. It's all the same kind of concepts. It's just a really stable position. You're not going to ever rearrange. All right, so there's one more reaction I'm going to cover, which is how do you reduce these? Because as I talked about previously, if you're to take, for instance, toluene, throw in H2 and platinum, you're going to get no reaction. There is a way to do it with H2. So if you were to take H2, throw in nickel at 100 atmospheres and 150 degrees Celsius, you can actually do this reduction. The problem is that this is just a huge bomb. you have extreme pressure, you have extreme heat. Like no one would ever do this reaction because it's more likely to just explode and kill you than it is to ever actually reduce this. So the way to get around this is to do a reduction using sodium, where we're going to pump some electrons into the system. And I'll go through the mechanism for it in a minute. So if I take sodium 0, which again is different than sodium plus, we think of sodium plus as like Na plus, O minus kind of a thing. Here we have a sodium with an extra electron to it, which makes it neutral because it's in the first column of our periodic table. And methanol and ammonia, this is going to be able to do a reduction to this diene here, which is no longer conjugated, it's no longer aromatic, so you just throw an H2 and platinum to get this product here. Okay, so let's talk about how this works. There's two different ways it can work. And it's going to depend on what substituent we have. So I'm going to draw with toluene first, and then we'll do benzaldehyde second, which will give you a different answer. So if I take toluene here, I throw in sodium, which has this lone pair of electrons. This electron can go into our ring. Our electrons are going to orient themselves like this. When you have a lone pair and you have a single electron, these are always going to dramatically repel each other. So they're always going to end up on opposite ends of your molecule. And realistically, there's two different options we could have. We could have this or this. Or we could have the negative here and the radical here, flip those around, and those are kind of the ways this could be. And either of them, they all kind of lead to the same thing. So the reason we don't have this one on the right is that this is a less stable double bond. It's only got two substituents here versus this double bond is more stable. It's got three substituents. Same rules as our like 1,2 versus 1,4 additions with cold versus heat. We've got a more stable double bond, a less stable double bond. So this one's going to form. From here, if we pick up NH from ammonia, technically there's two H's here, we can get this structure. Bless you. We'll have another sodium give us another electron. This is going to be our most stable resonance structure. Because these electrons can go up here or down here. Versus if I had this, my electrons can only go in one direction. So this one has two resonance structures it can make versus this only has one. Same thing if it goes at the bottom. This is technically our most stable resonance structure. So this will also lead to the next protonation step. And it's going to give us this here. So we always end up with these double bonds being on opposite sides of our ring. So I said that benzaldehyde is a little bit different. And that's going to have to do with the stability of this position here. So same reagents, Na, NH3 methanol is our solvent. Now when we do this reaction, we are going to form this electron configuration instead. So the last one, we prioritized the double bond stability. For this one, we get another set of resonance. This can now go out of our ring and have resonance to this carbonyl here. So having our negative at this position is going to be even more stable than it was to have that triple bond, or not triple bond, that tri-substitute double bond. So for this one, we're going to end up with stability here. We can grab this proton, do the same steps we just did, pick up another Na from sodium, or another electron from sodium. Grab an H. And make our final product. So to compare them directly, if I have something, I'm going to put like a sec-butyl group on here. This aromatic ring. Oh, I keep switching between ketone and aldehyde. Doesn't matter if it's ketone or aldehyde, they all get the same thing. This will give us a double bond pattern where they're opposite with one of those double bonds on our more substituted double bond position versus with a ketone or an aldehyde. I'll draw an aldehyde for this example. Last one I drew a ketone. We get the opposite double bond orientation where neither of them are attached to this more substitute position. All right, so that is everything for chapter 17. On Monday, we're going to start chapter 18, which is we're actually doing reactions that add things to different positions to our ring. they're going to have more complicated mechanisms to them. So we'll spend a lot of time talking about that. And I will see you guys on Monday. Question in the chat. Someone asked, how do you know where the electron will attack? So it's just going to be based off of building up stability. This is our most stable position here. We're going to end up with this negative charge in this position. So that's where it's going to attack. Technically, it could end up in these other positions. It's just less likely. So again, this is like a major product type of situation. This is our most stable position. That's where it'll attack. And then down here, this is again our most stable position. It's got two sets of resonance versus over here, which only has one. So it'll attack there, and that's why it gives us our more stable position. Yeah, so on the toluene, this is more stable. Technically, these two could be switched. Doesn't really matter which one's the negative, which one's the radical. We have the most stable double bond here, so that'll be when it attacks.